First thing that I want to talk about is the concept of spherical wrist. So spherical wrist is something like a shoulder joint. And no matter how complex the joint is, or no matter how complex the geometry is, when we are trying to solve it for robotics, what we are going to do is we will actually decompose the joint into some combination of uh, the rotary joint and the revolute joint. So at the end, it's going to be like rotary or revolute joint. So what I want to do is, I want to show you how this spherical joint looks like. So first, we have a revolute joint. The second revolute joint is perpendicular to the first revolute joint. First revolute joint. And the second revolute joint is perpendicular to the first revolute joint. And the third revolute joint is perpendicular to the revolute joint before that. And depending upon how you draw the kinematic diagram, the kinematics, visualization of kinematics would be easy or difficult. Now, what I want to show you is, think about it like this is the first revolute joint. And this first revolute joint is attached to the second revolute joint. And then the second revolute joint is attached to the third revolute joint. So we have this first revolute joint, we have the second revolute joint, we have the third revolute joint. And here we have the end effector. So this is the end effector. Now I want you to visualize an extreme case. The extreme case is if you have the first revolute joint, then you have the second revolute joint, and if you have the third revolute joint, I want you to understand that this revolute joint and this revolute joint are controlling 1 degree of freedom, which means what it means is no matter whether you rotate the first revolute joint R1 or you rotate the third revolute joint R3, the end effector orientation is going to remain the same. So this is called as the gimbal lock. Why is it called as a gimbal lock? Because you are losing 1 degree of freedom. So let me kind of explain this to you again. So if you have 3 revolute joints and those 3 revolute joints are perpendicular to each other, what that means is you are controlling the angular motion which is perpendicular to each other. So first revolute joint would control the motion about x, second revolute joint maybe control motion about y, and the third revolute joint will control the motion about z. But the problem is when the second revolute joint goes through 90 degrees, this is called as a 90-degree second revolute joint, first and third revolute joint become one. You don't have control of the third degree of freedom. So this is called as a gimbal lock. So this is called as the gimbal lock. So in gimbal lock, you lose 1 degree of freedom. And let me tell you, if you try to analyze the motion in this particular configuration, it will be very confusing for us to perform the forward and inverse kinematics. So the easiest way to do that is use a configuration that can be analyzed with the system that we studied. So for example, now as soon as I rotate this joint and I make this second joint horizontal, now I can analyze the forward and inverse kinematics. So what I'm going to do is I'm going to use the techniques that we studied. First, assign the coordinate system, then find out the rotation matrices, then find out the homogeneous transformation, and then multiply those homogeneous transformations to find out the values. One thing it is important to observe that this spherical wrist assumes that the relative distances between the joint 1, joint 2 and joint 3 are very small. In other words, like R1, R2, R3 are sort of on top of each other. Physically, that is not possible. There will be some distance, but by designing the joints, the actuators, or placing the joints and actuators, those distances are minimized. So when we are going to analyze, what we are going to do is we are going to assume non-zero distances. So as if I have a robot, wherein I have a robot with R perpendicular to R perpendicular to R. So I have a robot like that. But at the end, when I'm going to find out the homogeneous transformation, I would substitute all the distances is equal to 0. Everyone understood this? What it means is the first revolute joint will be on top of second revolute joint, on top of third revolute joint. So first and foremost, let's identify the Z directions. This is going to be Z0. This is going to be X0. And this is going to be Y0. Are you with me? Second, this is going to be Z1. And I want X1 that is perpendicular to Z1 and Z0. So I would say this is going to be my X1. And clearly, to complete the triad, this is going to be Y1. Are you with me so far? The next part, I need to add Z2. So I would say Z2 here. Then my X2 needs to be perpendicular to Z2 and Z1. Now, please note, no matter how I choose the direction for X2, X2 is not going to intersect Z1. Do you agree with me? So what I mean by that is if I draw my Z1, X1 here, or if I draw my X1 here, no matter, X2 here or X2 here, this X2 will intersect Z2, but it is not going to intersect X1, Z1. Are you with me so far? So what that means, it doesn't matter where I choose it. So for the sake of simplicity, I would use this over here. Now what that means, when we are going to perform the forward kinematics, we'll have to translate that frame. So this is going to be Y2. Are you with me? And just to be consistent, what I would do is, I would use Z3, Y3, and X3. Z3, Y3, and X3. Are you with me so far? Any questions about these frames? Now, what I'm going to do is, I'm going to assign the distances. This is going to be A1. This is going to be A2. This is going to be A3. And what we will do now is we will perform the forward inverse kinematics on this guy. So 0 R1, again this would be theta 1, this would be theta 2, this would be theta 3. 0 R1 cosine theta 1 minus sine theta 1 0 sine theta 1 cosine theta 1 0 0 0 1. You agree with me? What am I missing here? This needs to be multiplied with a projection matrix, and that projection matrix is the projection of new onto old. So which will be x1 y1 z1 x0 y0 z0. Are you with me? So x1 is aligned with x0, y1 is aligned with z0, and z1 is aligned with minus y0. Are you with me? So first row, first column, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column, first row, first column, right? Now I'm gonna use this for 0 h1. Will be cosine theta 1 0 sine theta 1 sine theta 1 0 minus cosine theta 1 0 1 0 0 0 0. And then the distance from the 0th frame to the first frame in the 0th coordinate frame. So this is going to be 0, this is going to be 0, this is going to be A1. And now technically, if you do use a spherical risk, you can just put all the values to 0 as translations, because at the end those would be on top of each other. But to solve the problem, let's set up the problem in a most general form. Now next question is, what is going to be 1R2? 1R2 is going to be cosine theta 1 minus sine theta 1 sine theta 1 cosine theta 1 0 0 0 0 1. Oh, theta 2. And here, now what we need to do is, we need to look at the projection matrix. The projection matrix is going to be, so I will write it over here, x2 y2 z2 x1 y1 z1. x2 is in the direction of y1, y2 is the direction of z1, and z2 is in the direction of x1. So when we perform this multiplication, I will write it over here. When you perform this multiplication, first row, first column, sine theta 2, first row, second column, 0, first row, third column, cosine theta 2, second row, first column, second row, second column, 0, second row, third column, sine theta 2, 0 1 3. Are you with me so far? Now one thing we need to understand, that the frame does not satisfy the rules. So the frame does not satisfy the rule. So what it means is we need to translate frame 2 to frame 1. Please understand. We need to translate frame 2 to frame 1. Are you with me so far? So what I'm going to do is I'm going to try to explain this once again here. This is my first joint, which is it gives me the frame X. What I have is X. No, this is Y1. This is Y1. This is Z1. And this is X1. And here is supposed to be the second joint. And then here, this is the third. So this is the end effect. So this is my joint 2. And this is my joint 3. Now there is one point which I want to discuss. That is very important. So initially, the frame was here. C2, Y2, and X2. Now please understand, the way this frame is set up, it does not satisfy the 4 rules. Can you see that X2 is perpendicular to Z2, but X2 is not perpendicular to Z1. I mean, X is not intersecting with Z1. Can you see that? Z1, X2 does not intersect Z1. Do you agree with me? To artificially make them intersect, what I need to do is, I need to translate this frame. Basically, this is going to be my X2, this is going to be my Y2, and this is going to be my Z2. Are you with me so far? So I got X2, Y2, and Z2. What that means is when I right now, when I write the homogeneous transformation 1H2, these two frames are on top of each other. So which means the relative displacement between these two frames is 0. So when I write this down, this is going to be minus sine theta 2, 0, cosine theta 2, cosine theta 2, 0, sine theta 2, 0, 1, 0, 0, 0, 0, and again 0, 0, 0, 1. And why is that? Is that because this frame number 2 is translated and sitting on top of frame number 1. Everyone understood this? Now, what we need to do is we need to go to the next frame, but there is something else I want to talk about. So check this out. This is frame X3, this is frame Z3, and this is the frame Y3. Are you with me so far? Now, I didn't explain this in a lot more detail in last class. What I want you to understand is when we are going to perform the analysis of 2R3 going from frame number 2 to frame number 3, you don't use this frame. Everyone understand? So this frame has effectively vanished. Now what that means is when I'm going to analyze, or when I'm going to write the rotation transformation, or when I'm going to write the the, the translation, what I need to think about is I need to think about x2, z2 and y2, which is translated, and x3, y3 and z3 at the end effector. Everyone understood this? So this frame is effectively gone. This frame does not exist. Now the implication of that is when you look at the projection matrix, you want to relate x2 to x3, z2 to z3 and y2 to y3. Everyone understood this? So when you are going to do the projection matrix, and that is the subtle advantage of the aligning the end effector frame to the previous frame, because your projection matrix becomes identity. You don't have to worry about, and that is a little tricky. Imagine if this would have been flipped, then what you have to do is you have to align this with this. So that's why the end effector frame is the replica of the frame before. So the process is, and there is something else which I did not emphasize in last class that I want to tell you, because I think this is the second problem or third problem where we are translating the frames, right? So second problem, okay. So note, this is A2 and this is A3. A2 and A3. So for practical purposes, this frame is gone. However, when we are going to look at the translations between this frame and this frame, when we are going to look at the translations between this frame and this frame, we have to find out the translations distances with respect to the old frame. Now, note, this is extremely important, and this I want to emphasize. Let me take a minute here to explain. X2 frame is attached to this joint. Sorry, X1 frame is attached to this joint. This is actually your R1, right? R0 was here. R0 was here. That is R1. So what that means is X1, Y1, and Z1. They are attached to the joint. That frame is not going to move if I rotate this angle. If I change this angle, my x2, y2 and z2, they are going to rotate. Once again, understand this is very important. So what that means is when I'm going to look at the translational distance, it should be about around z2. It won't be z2, it won't be like if this is theta 1, it won't be a2 plus a3 cosine theta 1 and sine theta 1. Are you with me so far? Let me explain this once again. So whenever you do the frame translation, please understand that the distance is along the new frame that we have translated. So we moved it over here. So once again, if I want to find out the relative distances between these two frames, it would just be A2 plus A3 along Z2. It will not be A2 plus A3 cosine theta 2 or sine theta 2. Everyone understood this? Why? Because this frame is attached to the body and it's going to rotate with the body. Are you with me so far? That is extremely important. So I will explain this when I am writing. So now I have to work on 2 R3, and since it's again going to be cosine theta 2 theta 3 minus sine theta 3 0 sine theta 3 cosine theta 3 0 0 0 1. And then here it's going to be x3, y3, z3, x2, y2, z2. So now again, this is going to be identity matrix because these two frames are aligned. Do you agree with me? The only problem comes is when you are doing 2h3, you will repeat cosine theta 3 minus sine theta 3, 0, sine theta 3, cosine theta 3, 0, 0, 0, 1, 0, 0, 0, 1. And please understand, this is going to be 0. This is going to be 0. And this will be A2 plus A3. And some of you may ask me, why not A2 plus A3 cosine theta or sine theta? Right? And the reason for that is, let me show you the rotated frame. What's happening with the rotated frame? Imagine so this is the first frame. So x1, z1, y1. And the rotation is theta 2. You agree with me? The rotation here is theta 2. When the theta 2 is 0, you agree with me that this new frame is aligned with this old frame. The new frame is aligned with this old frame. But when I rotate, what's going to happen is this frame, the new rotated translated frame, which is v2, x2, and y2 will also rotate. So if I provide, so let me use a different color. So if I rotate this, this is going to be theta 2, but this is going to be z2, this is going to be x2. Are you with me so far? Which means the now in this particular configuration, you are going to have A2 here, and then you are going to have A3 here, right? But still the distance is around z2. Everyone understood this? So, and z2 is the original frame. So this distance is distance everyone understood this? The last step of this problem is 0h3 is 0h1, 1h2, and 2h3. Yeah.
So what if we rotate the second frame?
Second frame, if you rotate, that doesn't matter because when you say second frame, which is x2, y2, z2, we all so first when we looked at the kinematic diagram, it was aligned. No, it was not aligned. They were separate. We translated it so that the rules meet. Actually, we meet all the rules. Then what that means is once I add a rotation transformation, which is of x2, the second frame gets rotated but stays with the joint. And which means this distance, which is along v2. Are you with me so far? So that is something that you should keep in mind. Same problem will occur if instead of that revolute joint, if I have a prismatic joint. I think that was the problem that we solved in the last class, right? So remember this, that whenever you rotate the frame, the distance between the frames need to be with respect to the old frame. So keep that in mind. Everyone understood this? Any questions? Any questions, concerns?
So this happens only when there is such a kind of treatment which is happening.
Whenever, so this will happen whenever the rules are not met.
Okay, when these when the rule and conditions are happening.
Yeah, when the rules are not met, this problem will appear. So whenever the rules are not met, just be aware of this case. Most of the times, this is the case that is gonna happen. So, and if you think about it carefully, why that is happening is because the z-axis for the next joint is basically perpendicular to the z-axis of the previous joint. If the z-axis of the next joint is perpendicular to the z-axis of the previous joint and is offsetted, no matter what you do, the rules won't be correct. Once again, I repeat. Why is this problem occurring? This problem is occurring because you have Z1, you have Z2, you have Z1 and you have Z2. They are perpendicular to each other, but they are not at the one and the same spot. They have an offset. Either it could be a horizontal offset, it could be a vertical offset. If that is the case, then you will have to translate the frame and you have to take into account this. Yeah.
So if we rotate the second frame, the first frame also rotate.
No, second frame, once we are moved on from the first frame to the second frame, we go from second frame to the third frame. We are not going to jump, so we have to follow this sequence because at the end, this is 0 to 1, there is no frame 1, 1 to 2 is basically a relationship between the first and second and third. Everyone understood this? Any questions here?
So like just now you said that if there is a translation happening, then this kind of A2 plus A3 kind of situation would definitely happen. It's kind of a rule or what?
Yeah, that will happen as long as you have the frame translation. You have to be very careful about the directions.
I mean,
Okay.
irrespective of the anyhow, it does not.
That will happen. Now, what I want to do is, the next part, if you want to solve this for a spherical risk, substitute all the distances is equal to 0, which means substitute A1 is equal to 0, A2 is equal to 0, A3 is equal to 0, perform the multiplication. And then you will get the equation for the spherical risk. Believe it or not, that's exactly what is happening in your Puma robot. One of the homework problems is the Puma robot. You agree with me? In Puma robot, you have the first revolute joint, second revolute joint, and third revolute joint. So first, so Puma robot. So side note, Puma robot is nothing but the first revolute joint, which is perpendicular to second revolute joint, which is parallel to third revolute joint. Do you agree with me? And after this, what you have is, you have R perpendicular to R, perpendicular to R. Are you with me so far? So if you think about your robot, this is the end effector of the Puma robot, and this is the actuator or manipulator. Manipulators. Everyone understood this? Now, next logical step is just to go on to MATLAB and work this out. Just go on to MATLAB and work this out. That is a very straightforward thing, and I'll show it to you. But there's an important point which I want to tell you. Imagine if you have a Puma robot. Imagine if you have a Puma robot. How would you solve forward and inverse kinematics? Do you agree with me? We have already studied the forward kinematics and inverse kinematics of this manipulator. So we have studied this, then this, and then this. So this you have so we have done the forward and inverse kinematics of this manipulator. Do you agree with me? Now, if you use what we have done now today, you have 0h3, which means you have the forward kinematics and inverse kinematics for the R perpendicular to R rest, right? So what you can do is you can multiply 0h3 for this manipulator multiplied by 0h3 for the spherical wrist. So this guy, or I can call this something like 3h6. So can you see that you get 0h6 for Puma? Everyone understood this? Which means if you combine what we did in the previous class along with what we have done here, you got the forward kinematics for the Puma robot. Everyone understood this? What does that mean? It means you specify the value for theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, and you will get an end effector position and orientation. Everyone understood that? You will get 0h6. 0h6. What is 0h6? 0h6 is nothing but 0r6, and then you have px, py, pz, 1, you have 0. So this gives you the end effector orientation. And this gives you the end effector position. Are you with me? Now I want you to understand forward kinematics problem has a solution. Substitute the values of theta 1 to theta 6. You are going to get this matrix and you are going to get this vector px, py, pz. Everyone understood this? The problem is the inverse kinematics may not have solution. And here, please understand. Let's understand the complexity of the problem. If I give you px, py, pz, if I give you px, py, pz, I have 3 equations, but I have 6 unknowns. Can you see? Theta 1, theta 2, theta 3, theta 4, theta 5, theta 6. I give you px, py, pz, and if I ask you to find theta 1 to 6, number of unknowns are more than number of equations. Means we won't be able to solve it. Everyone understood that? But at the end, here is the trick. We have px, py, and pz. At the end, we have px, py, and pz. Which means if I give you these 3 values, you can potentially find out r1, theta 1, theta 2, theta 3, or theta 4, theta 5, theta 6. So 3 equations you have to solve. You can find 3 unknowns. Do you agree with me? Now, how do we solve the inverse kinematics problem for Puma robot? Inverse kinematics problem for Puma robot can be solved if we make an assumption, and that assumption is not wrong. If we make an assumption, we say that manipulator, the manipulator is responsible for px, py, and pz. Manipulator is responsible for px, py, and pz. Everyone understood that? And the end effector theta 4, theta 5, theta 6 is responsible for the orientation. If you make that assumption, the inverse kinematics problem can be solved. What is the assumption we are making? Manipulator is responsible, which means theta 1, theta 2 and theta 3 are responsible for PU, PX, PY, PZ. So let me write this down. Inverse kinematics for Puma or for that matter any robot that has more than 3 degrees of freedom, or any robot more than 3 joints or 3 joints. So what we need to do is we have to use the assumption first 3 joints theta 1, theta 2 and theta 3 are responsible for Px, Py, Pz. Are you with me so far? And theta 3, theta 4, theta 5 and theta 6 are responsible for the orientation of end effect. Are you with me so far? Now, to solve this problem, let's try to think about the complexity of solving the problem. If I say theta 1, theta 2 and theta 3 are responsible for Px, Py, Pz, that problem can be solved, which would be the same as the inverse kinematics for R, perpendicular to R, parallel to R type of robot. So what you will do is, you would solve the inverse kinematics problem for the manipulator and get the values of theta 1, theta 2 and theta 3. You agree with me? Everyone understood this? Okay. Now, but when we are trying to find the orientation, understand the position and orientation problem is sort of coupled together, because the joint values that we found out for inverse kinematics or position are contributing to orientation. So what that means is, I want you to understand this very, very carefully. 0R6 is what? Is 0R3 and 3R6. Are you with me so far? So what it means is this final orientation is because of theta 1, theta 2, theta 3 and theta 4, theta 5 and theta 6. Are you with me so far? When I solve the inverse kinematics problem, I get the values of theta 1, theta 2, theta 3. You agree with me? Which means I should be able to find out 0R3. And what I need to do is 0R3 contains theta 1, theta 2 and theta 3. These are knowns. Do you agree with me? What I need to do is I need to take the inverse of this. So 0R3 inverse multiplied by 0R6 and I get 3R6. So please understand, this 0R3 inverse, it's an orthonormal matrix, which means inverse is equal to transpose. So I would do transpose multiplied by 0R6 3R6. So please understand, this guy is given to us. This is given to us. This guy we find from inverse kinematics of R perpendicular to R, parallel to R, and that gives me theta 1, theta 2, theta 3. Then I would take those theta 1, theta 2, theta 3 and substitute it over here. So substitute theta 1, theta 2 and theta 3. And now can you see that I have 3 equations and 3 unknowns. Actually, you have to work out the problem so that you understand what is happening here. So this is whenever you are solving an inverse kinematics for a robot that is more than 3 degrees of freedom, you have to solve that in the pieces. It means what you have to make the assumption that the first 3 joints are responsible for the position, and last 3 joints or whatever last joints are, they are responsible for orientation. So first solve the inverse kinematics for the manipulator, find the values of theta 1, theta 2, theta 3, substitute the values of theta 1, theta 2, theta 3 and find out 0R3. This is known in closed form, 0R3. Find the transpose. This 0R6 is the final orientation of the manipulator, or final orientation of the end effector. That is given to you. Because to solve the inverse kinematics, the position is given, orientation is given. It means Px, Py, Pz, this guy somehow is completely known. And we have to find out those 6 values. Everyone understood this? So there is a little bit of back and forth method technique that you have to use to actually get to solve the inverse kinematics of the Puma robot. But for that matter, any robot that has more than 3 degrees of freedom. So a simple example is the Dobot that you are using. And if I ask you to do the inverse kinematics of Dobot, then what you will have to do is you have to first solve the inverse kinematics of position, find those theta angles, use those thetas, theta 1, theta 2, theta 3, find the transformation 0R3, and then take the inverse of it and multiply with the final orientation transformation, and then you will get 3 equations and 3 unknowns that you have to solve. Everyone clear? Okay, for my own satisfaction, I'm going to write this technique. So first, convert the robot into manipulator. And manipulator means the first 3 joints. So in this case, we have theta 1, theta 2, theta 3, and wrist. Wrist comprises for theta 4, theta 5, theta 6. Second, solve inverse kinematics for manipulator based on position and get so Px, Py, Pz is equal to, this equation should give you theta 1, theta 2, theta 3. Or theta 1, theta 3 are there. Third step, use theta 1, theta 2, theta 3 and find 0R3. Everyone understood this? Next, 0R3, take the transpose, multiply this with 0R6. And please note, 0R6 will be given. Either it will be given in the form of roll, pitch and yaw of the end effector. It could be given in the form of the photonions. So this guy 0R6 will be known. Individual angles will not be known. but this matrix, which is full of 9 elements, will be known. There will be numbers. You won't know what theta 1, theta 2, theta 3, theta 4, theta 5, theta 6 contributed to that 0 R6. But at the end, they will tell you that this is known. So this is 3 by 3 matrix is completely known. And then what you do is you basically equate it to 3R6. And this 3R6 is in terms of theta 4, theta 5, theta 6. Are you with me so far? And you can actually solve it either using the solve, or you can just look at the matrix and solve the problem. Do you understand this? Any questions here? Okay. The next part which I want to introduce, but I will not spend a lot more time on this, but I just want to spend just introduce to you. Say, imagine I know the value of px, I know the value of py, I know the value of pz. Px is the function of theta 1, theta 2, theta 3. Actually, let me start with this. Say px is only function of theta 1. Py is only function f1 theta 1, f2 theta 2, and pz is f3 theta 3. Let me make it even simpler. So theta 1, and maybe theta 1. Okay, so I have 3 functions. If I want to find out the velocity, what I should do is d by dt of px. D by dt of px is going to be, please note, d by d theta 1 of f1 multiplied by d theta 1 by dt. You agree with me? This is u times v rule. This is u, v rule. U, v. Now this guy is, do you agree with me? This is theta 1 dot. Rate of change of angle is theta 1 dot. Now this is the derivative. I will have to repeat the same process for py and pz. Everyone understood this? Any questions here? Now imagine I want to give you an alternate scenario where px is function of theta 1 and theta 2. If px is the function of theta 1 and theta 2, what would happen? D by dt of px, can someone tell me? It will be df1 by d theta 1 multiplied by d theta 1 by dt plus d f1 by d theta 2 and d theta 2 by dt. Are you with me so far? Everyone understood this? Any question about the derivative? If I want to write this equation in maybe a matrix vector notation, I can write this something like this. Px dot is equal to df1 by d theta 1, df1 by d theta 2 multiplied by theta 1 dot theta 2 dot. Are you with me so far? Once again, first row, first column, df1 theta 1 dot, df1 theta 2 dot. You agree with me? Any questions here? Now what I want to do is, I want to ask you the same question. Instead of if I have something like py, if I have, I'm going to write it over here. So if I have py, which is function of, this cannot be the function f1, it will be a different function. Do you agree with me? But again, the variables or the dependent variables will be theta 1 and theta 2. Do you agree with me? If I want to write this, how can I write this? So please note, function f1 is related to px. Can you see that this f1, we are taking derivative with respect to theta 1, we are taking derivative with respect to theta 2. Since there are two independent variables, we are not going to take the full derivative, but we are going to take the partial derivative. So ideally, the way I would write this is, and why is it? Because there are two independent variables. So if I want to take the derivative out of those two independent variables, I need to keep one variable constant and I need to take the rate of change with respect to other variable. Everyone understood this? So this becomes partial f1, partial f1, partial f1, partial theta 2. Do you agree with me? If I do the same thing for py, this is going to be partial f2 by theta 2, partial f2 by theta 2. And again, it will be the same. So if you expand, you are going to get the same answer. So if I want to write this equation as a matrix vector equation, this will become px dot py dot, and this will become partial f1 by partial theta 1, partial f1 by partial theta 2, partial f2 by partial theta 1, partial f2 by partial theta 2, multiplied by theta 1 dot and theta 2 dot. Are you with me so far? So I want to give you sort of a simpler explanation to this. Think about it like you have a quantity, a function that is changing. If you want to find out the derivative, how would you find out the derivative? If you want to find out derivative, you find the slope. If you multiply that slope by the horizontal distance x, you get this distance y. Do you agree with me? Same thing is happening. The only issue is here we don't have just the change of theta 1, we have the change of theta 1 or change of x with respect to the time. That's what is happening. So that's why we have theta 1 dot, we have theta 2 dot. This term tells me how much of px is dependent on theta 1 dot, how much of px is dependent on theta 2 dot. Simple example, if you have $100, if I give you $1, it will be $101. But if I give you 1 cent, it will be $100 and 1 cent. Do you agree with me? Which means the contribution of 1 cent is significantly less compared to the contribution of $1. Do you agree with me? Which means if I were to add dollar, that is 100 times more powerful, or it adds 100 times more weight compared to if I were to add 1 cent. So, one second, how would you remember this? Px is given in terms of f1. So here, the numerator will always have f1, f1. Denominator will be responsible for theta 1 and theta 2. So, denominator corresponds to this, numerator corresponds to the main function. Everyone understood this? This is extremely important. And this is called as Jacobian. This guy is called as Jacobian. And this determination of Jacobian is very important. And if you were to do this in MATLAB, it's very simple to find Jacobian in MATLAB. And I will show it to you. Then, so now what it means is if I find out the Jacobian, if I multiply by the joint velocities, I get the end effector velocity. That's what it means. If I find the Jacobian and if I multiply by the joint velocities, I get the end effector velocity. But it is important to observe that this Jacobian is dependent on the instantaneous values of theta 1 and theta 2. So what I need to do is I need to use the values of theta 1 and theta 2 to find this Jacobian as numbers. Number here, number here, number here, number here. Multiply that by the instantaneous joint velocity, number here, number here. Then I get the velocities here. Everyone understood this? Every time that theta 1 is going to change, every time that theta 1 dot is going to change, which means at every time step, I need to calculate the Jacobian, I need to multiply that with the joint velocity, and I get the end effector velocity. Everyone understood this? This is the theory behind it. There are two types of velocities that we have to find. First is the translational velocity, Px dot, Py dot, Pz dot, and the rotational velocity, because understand that end effector is rotating. And we'll talk about the rotation velocities in next class, and then we'll try to work out the problem. But before we conclude for today, there is one question that I want to answer. Other method is for inverse kinematics, more than 3 joints. So there is a shooting method, numerical technique that may or may not give you the answer. So you can use a shooting method, or if you take again, there are additional techniques for finding inverse kinematics for more than 3 degree of freedom systems. So I recommend you looking at some advanced kinematics books. They will talk about how to find out how to solve the inverse kinematics for more than 3 degree of freedom robot. But this method it will work in the problems that we will deal in robotics 1 and robotics 2. Now what I want to do is I want you to go to MATLAB. Quickly go to MATLAB screen and download. I don't know if you already downloaded. There is an inverse kinematics code at my canvas. So if you go to my issue, sign in, go to robotics. Okay, this needs to be faculty. So I want you to go to robotic system 1. And by now we have looked at a lot of codes. So I just want you to look at this spherical rest code. And you are welcome to download this and quickly run and convince yourself that this code runs. But quickly, you have the spherical rest, and spherical rest only has 3 joints, theta 1, theta 2, theta 3. And then what we are doing is we have the first homogeneous transformation, we have the second homogeneous transformation, and we have the third homogeneous transformation. And please understand, I substituted A1 here, A2 and A3 here. Everyone understood this? These are the same homogeneous transformations that we found out. In the next part, what we do is multiply H03, which is H01, 1H2, and 2H3. And then if I substitute the values of theta, theta 1 is equal to 0, theta 2 is equal to 35, theta 3 is equal to 0, it will give me some forward kinematic solution. And in the last part, what I'm doing is I'm using the same forward kinematic solution to find the inverse kinematic solution. Did you understand this? This is the same script that we have used in the past. The only difference is the 801, 802, and 803. They are different. 0x1, 1x2, and 2x2. So please run this code and make sure that this code runs. So please solve this, and then you'll be able to get the values of theta 1, theta 2. But one thing I want you to understand is this one, and I want you to try this. Try to find out. Yeah, just run this code, and then you will notice that it's easier to first find the first two thetas, theta 1 and theta 2, and then you can just find out the values of theta 3. So just try to, if you have MATLAB open, just run this code. I need to show this code. So if you, because this is the problem with the spherical wrist, I want you to understand. If you follow the technique that we discussed last class and just blindly follow it, you are not going to get the correct answer, because these equations are not suited well for direct application of MATLAB solver. So let me run this, and then, okay. So copy this and run this. And if you use the technique that we used earlier, remember theta 1, theta 2, theta 3, directly solving three equations simultaneously, your solution will be inaccurate. That won't be an accurate solution. So what you will have to do is, you have to first find out the values of theta 1, theta 2, and then you have to find out the theta 1, theta 2, theta 3. So I would encourage you to try that. If not, I will discuss this in next class briefly.